So let's just jump right in. When I say the word entropy, what's the first thing that pops into your head? For most of us, it's probably chaos, mess. The idea that everything is always falling apart. But what if I told you that's, well, not really the whole story? What if that's a seriously incomplete and kind of misleading picture? Today, we're going to look at what entropy really is.
In this right here is the key. This is the whole idea we're going to unpack. A physicist named John Bayes put it perfectly. Entropy isn't about how messy something is. It's a measure of our ignorance. It's literally the amount of information we're missing about a system. It's not disorder. It's just stuff we don't know.
To make this real, just look at this number, 23 bits. What is that? Well, that is roughly the amount of information we are missing about the precise microscopic state of one single hydrogen molecule just floating around at room temperature. But seeing a number that specific, well, it raises a pretty huge question.
Right? It sounds like a total paradox, doesn't it? How can you put a precise number on what you don't know? How do you quantify your own ignorance? Well, that is the exact mystery we are going to solve in this explainer.
So this is where our journey begins. We're starting with this really specific, tangible puzzle. We're going to figure out how in the world scientists can so confidently say there are 23 bits of information we're missing locked away in one of the simplest things in the entire universe. But before we can count the information we're missing, we have to figure out how to count information at all. I mean, what does it even mean to say something has an amount of information? To get there, we first have to see how information can be measured as a number. And it all boils down to this really simple but incredibly powerful formula. The amount of information you get when you learn something happened is related to its probability, p. And what this means is kind of cool. The less likely something is to happen, the more information you get when it does. Think about it. A dog bites a man. Not much information there. But a man bites a dog? Whoa! Now that is a headline. That's a lot of information. And this brings us to our fundamental building block, the bit. A bit is just the amount of information you get from a perfectly even 50-50 chance. So when you learn the outcome of a fair coin flip, whether it's heads or tails, you've gained exactly 1 bit of information. Then it just adds up from there. 3 coin flips, 3 bits of information. It's our basic unit of measurement. Okay, so coin flips are a good start. But to really get your head around the mind-blowing scale we're talking about, let's use a different example. A regular old aluminum license plate. We're going to look at 2 very, very different types of information connected to it. So on the one hand, you have the information that's written on the plate, the letters and numbers you can just read with your eyes. But on the other hand, you have the information that's in the plate. I'm talking the exact position and motion of every single atom that makes up the physical thing, and these are 2 vastly different concepts.
Let's start with the easy one, the information on the plate. For a standard 7-character license plate, it works out to about 36 bits of information. That's a number we can handle, right? It's like knowing the results of 36 coin flips. No big deal. Now, for the information in the plate, the missing information about the microscopic state of all those atoms is about 1.6 times 10 to the 25th power bits. I mean, that number is just staggeringly huge, and this shows the difference perfectly. The 36 bits is just data. That colossal number, that is thermodynamic entropy. It's the information hidden in the microscopic world we can't see.
Okay, so now that we've got a feel for information as a number, we can bring it all back to entropy. We're about to see how entropy is really just the average amount of information that we're missing about something.
This idea is called Shannon entropy. It's not about the information you get from one specific outcome. It's about the average information you'd expect to get if you kept doing the same experiment over and over. And another way to think about it is that it's a measure of how spread out or how uncertain your probabilities are. And this chart makes it really obvious. If you have a fair coin, your chances are spread out perfectly, 50-50. You are maximally uncertain about what's going to happen next. That's high entropy. But if you have a biased coin that lands on heads 90% of the time, you're a lot more certain, right? The probabilities are all bunched up, so the entropy, your average missing information, is low.
This all leads to a really important practical question. In the real world, we hardly ever know all the facts. We usually just have a little bit of information, like maybe an average value of something. So given that, what's the most logical way to make a guess?
The answer is something called the principle of maximum entropy, and it's basically a rule for making the most intellectually honest guess you can. You look at all the ways things could be that still fit the few facts you know, and then you pick the one that has the highest entropy, the one that leaves you the most uncertain. It's a way of making sure you're not pretending to know things that you don't actually know.
Okay, this is where it all comes together. We've been talking about abstract stuff, like information and probabilities. Now we're going to slam that right into the physical world of energy, temperature, and actual molecules.
And this is what you get if you take a physical system and the only thing you know for sure is its average energy, and then you apply that principle of maximum entropy. The most honest probability distribution you can come up with is this, the Boltzmann distribution. This equation isn't just pulled out of thin air. It's the direct result of being honest about our ignorance.
So what is this formula really telling us? Something really simple, actually. It says that for things in thermal equilibrium, being in a really high energy state is exponentially unlikely. And temperature, that T in the equation, is like a control knob. When it's cold, that probability drops off super fast, so things stay in low energy states. When it's hot, the drop-off is more gentle, and those higher energy states become easier to reach.
And with that, we now have all the tools we need. In this last section, we're going to take this whole idea, this information-based approach, and use it to make a real, testable prediction about our hydrogen molecule and see if any of this actually holds up in the real world.
Now, one of the really powerful results that comes out of all this thinking is a fantastic shortcut called the equipartition theorem. It basically says that for a lot of simple systems, nature is really fair. On average, it gives every possible way a molecule can move or store energy, every degree of freedom, the exact same little slice of energy, 1/2 kT.
So, let's just count them up for our hydrogen molecule. It can move left and right, up and down, forward and back. That's 3 degrees of freedom. And because it's shaped like a little dumbbell, it can also tumble end over end in 2 different ways. That's 2 more. So, 3 plus 2 gives us a total of 5 degrees of freedom.
And here it is, the moment of truth, the payoff for all of this. Using our theory, which, remember, is all based on maximizing our missing information, we predict that it should take 3.45 times 10 to the minus 23 joules of energy to raise the temperature of one hydrogen molecule by 1 degree. So what happens when you go and measure it in a lab? You get 3.39 times 10 to the minus 23 joules. I mean, that is absolutely stunning. They're nearly identical. Our purely theoretical model, based on admitting what we don't know, gets the real-world physics almost perfectly right.
So, the big takeaway here is that entropy isn't some vague idea about messiness. It's a hard, physical measure of missing information. And by starting with that one idea and following it to its logical conclusion, we can make incredibly accurate predictions about the real world. In fact, this is exactly the kind of logic physicists use to work backwards and arrive at that 23-bit number we started with. And that just leaves us with one final, fascinating question. If this way of thinking can correctly predict the energy of a molecule, what other mysteries, from the beginning of the universe to the nature of life itself, can we start to solve just by asking that simple question? How much information are we missing?